Okay, welcome back to the ChemDoctor, and this is the 8th video in the series on gases. And in the previous video, what we did was we learned about the fact that at standard temperature and pressure we can define the volume of 1 mole of gas being exactly 22.41 liters. So let's review a couple of those concepts. So number one, in the previous video, we defined STP, and this is what we call standard temperature and pressure of a gas. All right, and the standard temperature and pressure of a gas is defined where T is equal to 273 Kelvin or 0 degrees centigrade, and the pressure is equal to 1 atmosphere. Now, if we further stipulate that we have exactly 1 mole of a gas, and this would be 1 mole of any gas. It doesn't matter whether it's like nitrogen or oxygen or even a gas mixture like air. If we have exactly 1 mole of particles, you can use the ideal gas equation, which I think I'll go ahead and put over here in the corner. So PV is equal to nRT. You can use the ideal gas equation to calculate the gas's volume, and if you do that, what you're going to get is 22.41 liters. And this relationship offers you a unit multiplier when we're dealing with any sort of gas situation which is defined at STP. Now, the thing about stipulating that the temperature and the pressure of a gas is constant is that you will have some kind of relationship like this at any temperature and pressure that's fixed, but it won't be a situation where exactly 1 mole is equal to 22.41 liters. The reason I'm bringing that up is because if you're approaching a problem that involves stoichiometry, for example, and I will produce some videos that give you some examples of this, where the temperature and pressure are fixed. You need to understand that Avogadros' law, and that's the law of combined volumes, where he has shown that equal volumes of a gas at a fixed temperature and pressure have equal numbers of particles. You will have some kind of relationship like this that will hold up for those conditions. Now, chemists have defined STP, though, as being a very specific set of conditions where the temperature is fixed at 273 and the pressure is fixed at 1 atm. And under these conditions, then 1 mole of a gas is 22.41 liters. Now, we can use this idea to take the properties of a gas even further. So let's say that we have exactly 1 mole of nitrogen gas. All right, and if we have exactly 1 mole of nitrogen gas, we can determine its molar mass easily, because 1 mole of N2 will give us a molar mass that's going to be about 28.02 grams per mole. Now I want you to think about this concept for a minute, because we have literally on the screen we have literally two kinds of molar concepts. In this situation here, where I've defined the volume of 1 mole of gas at STP, this is what we call molar volume. Molar volume. So this is literally the volume of 1 mole of gas. In the second part here, we've defined molar mass. All right, and this is a concept that we've dealt with before, actually in many different videos. And molar mass is literally the mass of 1 mole. So now if we combine these two concepts into one, you can see that we can actually determine the density of an ideal gas. All right, the density of an ideal gas, because since we know that 1 mole is 22.41 liters, and we take this a step further and say, okay, well, we have 1 mole of nitrogen gas, then we can figure out the density of this gas simply by taking the 1 mole of nitrogen and realizing, okay, that's equal to 28.02 grams, all right, and at STP, the same mole of this gas is going to be in 22.41 liters. And so if we take a ratio of its mass to its volume, all right, and I haven't really ditched the mole here. If you put this over a mole here, and you put this guy over a mole here, you can see what happens is that the moles are going to cancel out. All right, and what we're going to be left with are the units of grams per liter, and the density of this particular gas is going to be 1.25 grams per liter. Now, if you're a chem student who's used to thinking about density in terms of solids and liquids, you'll notice that the volume parameter here is in units of liters, and that has to be true for a gas because gases are expanded by comparison to a solid or a liquid. So in the case of a solid, your density units are going to be grams per cubic centimeter. In the case of the liquid, it's going to be grams per ml or milliliter. But in the case of the gas, it has to be grams per liter. Now, we can actually come up with a generalized formula for this, where we can relate the molar mass of any unknown gas to its density by manipulating the ideal gas law. So what I'm going to do to finish the video is we're just going to quickly derive a general equation that we can use to solve for the density, or literally the molar mass of any gas. So density and molar mass. All right, so the first thing we're going to do is take and we're going to divide our equation both sides by the volume. So we're going to have pressure is equal to, now what I'm going to do is I'm going to isolate where I put the V. So I'm going to put it underneath the N, and I'm going to just slide the RT over a little bit. So that, because what I want to emphasize here is this ratio of moles over volume. Now, if you've kept up over the many videos, you're going to notice about this quantity here that it's something special, moles over volume. This is essentially molar concentration. Molar concentration. And what we're going to do now is we're going to come up with a substitution that we can put in for the N. So remember that your N is equal to moles. And what I'm doing here is I want to take this N divided by V, which is essentially molar concentration, and I want to change it into a relationship where we can get the density and we can get the molar mass to fall out of this thing. So remember that moles, using unit multiplier method, is going to be equal to the grams of any substance divided by its molar mass, right? And here's what this is going to look like if I took the units, if I took the molar mass part of this right here and I split it into its units. This would be the grams of the substance divided by grams over mole. And you can see that if we carry out the math, that we're going to literally arrive back at this quantity. So what we're going to do now is we're going to take this thing right here and we're going to substitute it in for the N. So the new equation is going to look like this. It's going to be P is going to be equal to grams over the volume times RT over molar mass. Now, I'm trying to simplify this. If this looks a little strange to you, what you should do right now is pause the video and take yourself through the algebra so you can see that literally all I did was take the G over molar mass and substitute it in for the N. Now, we can further substitute this, and we can further manipulate this, excuse me. We're going to further manipulate this, and what I'm going to do is I'm going to multiply molar mass now times both sides of this equation. And the new equation is going to look like this. So I'll make this an arrow instead of an equal bar. So we're going to have pressure times the molar mass of the gas, and this is going to be equal to grams over the volume times RT. Now notice that grams over volume, okay, this is the density. So that's where the density of the gas came from. And I want to remind you, or I'm going to take you back. I know I have a lot of arrows here, but I'm going to take you back to this relationship right here, where I showed you at the beginning of the video at under conditions of STP, where we have 1 mole is exactly equal to 22.41 liter, that we can do a simple substitution with the molar mass of the gas, and we can get literally to the density of that gas. All right, so this is the density of the gas, coming back to the formula. So the final version of this equation is going to be equal to the pressure times molar mass is equal to the density of any gas times RT. This is a very important equation. You should either know how to get it or be able to extract it out of your memory so that you can use it to solve various ideal gas equations where the problem involves the molar mass of a gas and the density. And in subsequent videos, we're going to do some examples of this. All right, so with that, I'm going to go ahead and close the video.